coming through loud and clear. We're doing this live, and live means that there are all sorts of things that can go wrong. So hopefully you're hearing me and seeing me. And I'm going to assume that that is the case. And those of you who are new to this little series that we've been running, it's called Your Daily Equation. And, the point of it is, look, we're all dealing with this difficult, tragic situation right now in the world. And we have to pay close attention to all of the difficult, painful details. But it's nice to be able to pull away from those details every day for just a little bit. Some people will get a sort of mental relief through comedy, some through music. I don't know how many of you have seen this wonderful version of the opening song to Hamilton that the original cast did on YouTube, which is really just quite wonderful. That for me was a great mental break. But what we do here is not use music or comedy per se, but rather equations, things that tap into the deep truths of reality to give us a ability to kind of step away from the difficulties of the moment and connect with something that transcends ourselves. So that's what this is all about. And this is the live session in which I'm here to answer any and every one of the questions that I can get to in the limited time that we have. And it's great to begin by just sort of having people weigh in and let us know where you're from. I think some people in the chat already began to do that, but I kind of love to see the different countries scroll by. I saw Copenhagen, I saw Germany, India, others. So, we're kind of this little global community of people who care about these kind of esoteric ideas that really tap into some of the most important ideas that we have ever developed as a species. All right, so we see Canada, Belgium, Ontario, Romania, Morocco, Chicago, Staten Island, Holland, UK, India, Poland, India. Great, fantastic. All right, so let's actually jump right into the first question that I have here, which is from Jones Philip or Philip Jones. Don't know the right orientation of the name. What do you think will happen after we find a unified field theory? Will a new arena come up, or will it be the end of theoretical physics? And yeah, I mean, that's an important question to ask. There are those who may recall that Albert Einstein had this dream of finding what he called the unified theory. And a unified theory was meant to, in essence, be a master principle, a master idea that might be articulated in a single master equation that would be able to describe everything in the physical universe. And so the natural question that Jones Philip or Philip Jones is asking is, well, if you have that, is that the end of physics? You sort of have the final answer. And I would say it would be the end of one particular chapter in physics. And that chapter is the chapter in which, for a very long time, we have been searching for the fundamental ingredients and the fundamental laws that govern those ingredients. And if we had this unified theory, it might be the final chapter in that long story, right? The reductionist account of the universe might be on full display if we had the unified theory. But would that be the end of science? Certainly not, right? Reductionist accounts giving you the fundamental laws and the fundamental ingredients need then to feed into a synthetic account, a synthesis of the ingredients so that we understand how they come together into all manner of structure in the world, right? How do they come together into, for instance, living systems? We don't fully know the answer to that yet. How do those ingredients come together into conscious beings? How do they yield the ability to reflect and feel and sense things about the world? How do those ingredients come together and yield the fabric of space-time? How do they interface in the most complete manner with extreme objects in the universe, like black holes? So these kinds of questions will carry on for a very long time. And the one thing to bear in mind is the history of science teaches us that every time you gain a new insight, it allows you to ask questions that you couldn't even imagine asking. You couldn't even think of the questions until you had the advances necessary to formulate those questions. So I see this as an ongoing process that will just continue this trail of discovery for as long as we cogitating beings are here to think and to care about it. All right, Daniela Herbert. How would you describe the fundamental differences between physicists and engineers, specifically mechanical engineers, and how can we improve collaboration between our two fields? Yeah, so physicists, and I'm going to speak as a theoretical physicist so I can make this more personal. We're dealing in a world largely of equations and mathematics and trying to create and develop equations that are ever more adept at describing things that we see in the world. And we've done a really good job, right? We understand many of the fundamental particles, we understand electricity, magnetism, and all manner of forces that are at work guiding how these particles come together. Engineers tend to focus more on using the insights of science to make things, to build things. And if I'm going to be completely honest, I certainly have what might be called EE, engineering envy, right? I mean, I envy people who understand the science so well that they can put it into practice and create things. I kind of wish that I could do that. I can't, or at least I've never really tried. I always thought I never had the ability to do anything but the mathematics and the equations. But there's a depth of understanding that you have to be an engineer, because it's not a matter of just making it work on paper. It's got to work out there in the real world. So I think there are many opportunities for the two fields to work together. If an engineer is stumped on some theoretical calculation, perhaps gaining the assistance of a theoretical physicist would help push that program forward. And on occasion, physicists like me do want to see the ideas we're developing put into practice. In fact, you may not know this, and I think this is not apocryphal. So I hope I'm not spreading some like silly internet rumor. I believe I've got this knowledge from a reputable source. Yeah, I believe it's true. I'm pretty sure that Albert Einstein, yeah, I'm quite sure about this. Albert Einstein had a patent for a certain kind of refrigeration system, right? So here's the guy who's thinking about quantum mechanics and general relativity and special relativity and all the beautiful equations of 20th century physics. And he was able to cross the divide and think about real things in the real world. So the fields don't need to be separate. And when they come together, I think it's a potent way to put powerful theoretical ideas into real world practice. So good question. Martha Guadalupe del Consuelo asks, besides string theory, what other theory do you like most to explain similar things that string theory is trying to answer? Yeah, I mean, right. So string theory is a theory that I work on. It's meant to try to be the unified theory that Einstein was looking for. But we don't know if string theory is right. It could be that it's the final unified theory. It could also be a figment of string theorists' imagination, mathematical imagination, that's kind of a chimera that doesn't actually have any substance. It doesn't have any ability to really describe things in the real world. It might work on paper, but it might not work in practice. It's sort of a version of the engineering question, right? So it could be a theoretical idea of no real consequence to understanding how the world works. I hope that's not the case. I'd like to think that what we're developing in string theory really does have some impact on our understanding of the real world, but we don't know yet. So, what are the competitors, right? In a situation like that, you hope that there are competitors, and there are other theories. Loop quantum gravity is probably the most developed other approach to putting gravity and quantum mechanics together. That would be kind of a beautiful answer to how these distinct approaches fit together. You might say, well, you're just, thinking in too grandiose a way. It's not as though ultimately string theorists and loop quantum gravity folks are going to all hold hands around the campfire and hum the unified theory, right? That may just be a pipe dream. But on the other hand, each theory has its own successes, and maybe in combination, they'll be able to do what the individual theories on their own are unable to. So I don't think it's a ridiculous outcome to imagine, but certainly we're far from it today. Neelam asks, is it possible that dark energy might exist in higher dimensions? In interviews, talk about time travel being a real quality of physical law. My question is, are you being hyperbolic, or is time travel actually possible? So that's a good question. And maybe I should quickly say that I really, truly try not to be hyperbolic in interviews. I naturally get excited about ideas that I feel passionate about, but it's very rare. I mean, I'm sure somebody can dig up some interview where I will violate what I'm about to say, but it's very rare that I say something that I regret or that I say something that when I reflect back on it, I'm like, whoa, I kind of went mathematical equation, your daily equation after all, why not? So let's see if I can bring up some good. So, hey, hi, there you go. So, you can be quantitative about this. And if you take your velocity v to be, let me just sort of pick a good number, a number that's really close to the speed of light. So take 0.999999. So six nines right there. Let's go to nine nines and then like that times the speed of light, really close to the speed of light. If you then calculate this factor called gamma, which is 1 over the square root of 1 minus v over c squared, you just put this into a calculator. I'm not going to do the arithmetic for you, but this is on the order of a factor of roughly 200,000. This is an example that physicists like to use. I hope I've got the right nines in there, but feel free to correct me if when you plug it into a calculator, you get a different answer. But I think that's correct. And what this means is that when you step off the ship after that 1 year round trip journey, it will be 200,000 years into Earth's future. You will not see Earth in the year 2020, 2021. You will see it in the year 200,020, 21. Right? So 200,000 years later. And that is not something that's disputed, right? This is our understanding of how physics works as given to us by Albert Einstein. So yeah, that's a real kind of time travel to the future. Again, travel to the past, I don't have much to say about it. There have been proposals, but it's not something that anybody, I think, really puts much stock in today. And I appreciate that question because I think, I could be wrong, but at least in America, I think this is National Sibling Day, I think, something like that. So the little scenario I just told you, you can imagine two twins are on planet Earth, and one twin goes off into space and undertakes that journey and comes back. And that twin will be very young compared to the twin that stayed on Earth. In the example I described, the twin on Earth would age 200,000 years during that 1 year travel time. Okay, good question. All right, what do we have here? Sanjal Prasad. What was before the Big Bang? Yeah, it's a question I'm frequently asked, and one possible answer is there was nothing before the Big Bang in the sense that the whole concept of before assumes that there's a kind of time, a notion of time that's relevant before the Big Bang happened, but it could be that time itself begins at the Big Bang, and therefore the notion of before doesn't have any meaning there. Another possibility is that the Big Bang may not have been the beginning of time. It may have been the beginning of the realm that we inhabit in a larger space time, but there could have been events that happened before the Big Bang. In fact, in inflationary cosmology, the suggestion is that our universe, our Big Bang, may be one among a collection, maybe an infinite collection of Big Bangs, each giving rise to their own separate expanding realm. In which case, our Big Bang is just one event. And there are other bangs, other universes, and that might be another answer to the question of what happened before other Big Bangs. Okay. Mark asks, why aren't we impacted by the expansion of the universe? If the space between galaxies are increasing, space between galaxies is increasing, why isn't the space between molecules or atoms increasing? Good, 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 good. And there's a very straightforward answer to that question, which is this. So our bodies and molecules and atoms are held together largely by the electromagnetic force. The nuclei of atoms held together by the strong nuclear force. Let's focus just on the electromagnetic force for now. The electromagnetic force is far more powerful than the force of gravity. How do you know that? Well, look at this. I can pick up my Apple Pencil, whatever it's called, right? The entire earth is pulling on this Apple Pencil, and yet my puny little arms, which are moving under the electromagnetic force that is governing how my muscles contract and so forth, my puny muscles overcome the entire gravitational pull of a planet, of the earth. And that shows you that the intrinsic strength of gravity is very small compared to the intrinsic strength of the electromagnetic force, which means as space expands, which is ultimately a gravitational process, the electromagnetic force holding together molecules and atoms and human bodies is far more powerful than that outward spreading. And that's why we hold together. Now, it's not necessarily the case that this will always hold true. There are versions of cosmology in which the expansion of space is not only speeding up, accelerating as it is today, there are versions of cosmology in which the acceleration accelerates. The outward push that's driving everything apart, it gets stronger over time. And if that's the case, then it's possible that in the future, the outward push will be stronger than the electromagnetic force that holds things together, in which case planets may ultimately blast apart, human bodies may blast apart, even molecules and atoms may get ripped apart. It's called the Big Rip scenario. And so we don't know if this is the case. Measurements are currently underway to figure out if the so-called dark energy, which we believe is pushing everything apart gravitationally, to determine whether the dark energy is gaining strength over time. If it is, this is the fate that might await us in the future. So right now, no worry that the expansion of space is going to blow us apart. In the future, that may not be the case. Okay, let's see what we got here. Andrea Climbing says, would the probabilistic nature of quantum mechanics argue against a deterministic universe and in favor of free will? And yeah, I mean, it's a natural thought to have, because in the Newtonian universe, where we learn back in school, right, that you tell me the positions and the velocities of the objects, the ingredients, the particles, and you plug in the forces that are acting upon them, and you use Newton's F equals ma to figure out how those ingredients will move over time. And that way you can predict with certainty how the universe will be configured tomorrow based on how it's configured today. So with such rigidity in the unfolding of the universe, there appears to be no room for free will. So some people come along and say, well, that's true in a classical Newtonian world, but come on, we don't live in that world. We live in a quantum mechanical world in which the progression from today until tomorrow is governed by different considerations, governed by the considerations of probability, right? The laws in quantum mechanics don't tell you where things will be based on where they were yesterday. It tells you the probability of where they will be tomorrow based on where they were yesterday. And some think that, well, that slackening of the deterministic reins allows free will to come in and grab hold and steer the cosmological unfolding, or at least the human level unfolding within the cosmological unfolding. And I think that, based on what we know today, is not correct. Because even if you've got probabilities governing how things unfold, that's not what we mean by free will. Free will is your ability, or my ability, to be the ultimate originator of decisions, thoughts, actions. And if those decisions, thoughts, and actions are ultimately controlled by probabilities, someone in essence flipping a coin, well, that kind of random unfolding is not what we mean by volitional will, volitional control. So I don't think the probabilities of quantum mechanics, even though they loosen the Newtonian determinism, they do not allow for free will to enter back into the story. So the way I say it is, It doesn't matter what the laws of physics are. Classical, quantum, I kind of don't care what they are for this question. If the universe does progress via a lawful progression that is determined by laws, whatever those laws might be, if those laws are impersonal, if they don't involve the human will or human psyche as intrinsically part of those laws, then there's no place for human will to get in on the action because the laws, whatever they may be, determine how things unfold. And that's it. That to me is the end of a certain kind of free will. I don't think it's the end of free will totally, though. But if you want to know more about that, you're going to have to ask me. That's a separate question. All right, what do we got here? Blah 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 blah. What do we got here? What were the so this is Shalendra Kumar. What were the problems physicists were struggling to combine gravity and quantum mechanics together? Why is it so hard? Is what Shalendra is asking, to put gravity and quantum mechanics together. And the answer is that gravity and quantum mechanics, as formulated by the general theory of relativity and the probabilistic laws of the quantum realm, they rely on radically different views of reality. In the Einsteinian description of gravity, gravity is described by warps and curves in the space-time geometry. And that geometry is sort of nice and gently curving, and you've seen the imagery. The sun warps the fabric of space and the earth kind of rolls around that indentation. That's Einstein's image. Quantum mechanics has a completely different image of the fundamental nature of the world. You've got the uncertainty principle, which tells us that there are qualities of the world that are fundamentally uncertain, which means that they fundamentally fluctuate. They chaotically meander among a whole realm of possibilities consistent with our limited knowledge that is imposed by the uncertainty principle. And that chaotic world is completely at odds with the gently curving world of the Einsteinian geometrical approach to gravity. So concretely, if you were to examine a region of space, I'll put it right in front of my face right here, a region of space right here, you were to zoom in on it and look on fantastically small scales, according to quantum mechanics, that region of space would not be gently curving. It would be wildly undulating, fluctuating, sort of like the surface of a violently boiling pot of water. And that chaotic version of space is incompatible with the smooth image of space on which Einstein bases his theory of gravity. And so we have been struggling to blend these two pictures for decades, and at least on paper, we believe that string theory may be the theory that blends them together. But as I said before, we don't yet have observational or experimental evidence that supports that conclusion. And therefore, the best we can say is that on paper, we've got a theory that seems to work. We don't know if that on paper mathematical theory is relevant to the real world, relevant to reality. Mr. X asks, is space like a souffle? It depends on what kind of souffle you have in mind, Mr. X. But I think I understand what you have in mind. A souffle is, a structure that has all sorts of holes in it, all sorts of bifurcating qualities within it. And it could be that on the fundamental length scales, that space might have that kind of quality, and that the smooth space that we know about in everyday life may be an approximate average version of space that becomes relevant on large scales, but may not accurately describe how things look on small scales. And maybe a souffle is a good way of thinking about that. What do we have here? Okay, hello, Professor Brian, sir. This is Priyanashu. We know photons have energy and momentum, but how can that be if they are massless? Yeah, right. So you can say, E equals mc squared. If m is equal to 0, then E is equal to 0, done, right? So any massless particle can't have any energy. But if you looked at the first video that we did in this series, I hate to refer back to things that maybe you haven't seen, but what I really mean is go back and look at the first video called equals mc squared. And then also look at another video. Oh, goodness gracious, I can't remember which one it was off the top of my head, but there's another video which I talk about modifications to equals mc squared when particles are massless, because the derivation, or at least the explanation that most of us give for equals mc squared, the rest mass of a particle must be non-zero for that discussion to go through. In the circumstance when you're allowing particles to have zero rest mass, equals mc squared takes on a different form. I'll tell you what it is. It's E squared equals P squared C squared plus M naught squared C to the fourth, where M naught is the rest mass. And if M naught is equal to zero, as it is for a photon, you still have E squared equals P squared C squared, or E equals P times C. So for a massless particle, we learn that the energy and the momentum stand in a particular relationship, E equals P times C. But E can be non-zero and P can be non-zero. The momentum of a particle can be non-zero even if it is massless. So even when a photon slams into something, it can exert a little force by the change in its momentum, F equals dp dt, after all, if you allow me to speak in a little bit of math language. And indeed, the idea that a photon has momentum is experimentally true, it's mathematically true, even though a photon is believed to have zero rest mass. Okay, what else do we have here? Lila asks, is time conscious, or do we give time a consciousness? I will interpret that to mean, is time a fundamental part of reality, or is time something that we conscious beings impose on the external world in order to make sense of experience? And I have to say, Lila, I don't know. I really don't know the answer to that question. I wish I did know the answer to that question. I can maybe use one of my lifelines right now. I'm going to poll the audience. How many of you think that time is fundamentally stitched into the workings of reality? And how many of you think that time is something that conscious beings like ourselves impose on the external world? I can argue both ways, right? As a physicist, I see time intricately interwoven with every explanation that we give for how physical processes unfold. In fact, the very word unfold assumes that there is a kind of temporal quality that allows that unfolding to take place. On the other hand, I can imagine, it's tough, but I can imagine that time is a concept of our own making. And maybe we could think about the world in a more Einsteinian block universe approach, where you think of all of space and all of time just existing. There isn't any unfolding. All events are just out there in a big frozen river of time. The river of time doesn't flow, it's frozen, and every event just exists at a given moment at a given location. And it's only we conscious beings who are within that frozen river, we somehow have this ability to connect different events. And in that way, I'm about to sneeze, excuse me. Phew. Oh, gosh, this never happened to me in this sort of circumstance before. Maybe it's a connection between that and the frozen river that I was referring to. But if the frozen river picture true, maybe it's just conscious beings within that frozen river invent a notion of time in order to organize the various events into a coherent account. I don't know. I don't know the answer to that question. Okay, what do we have here? Andre asks, can an electron exist in multiple locations at the same time? And look, Andre, we often use that loose language in talking about quantum mechanics, right? We often say that the weirdness of quantum mechanics is that an electron, say, has a 30% chance of being here and a 70% chance of being there. And what that sort of means is we say it's like it's at both positions at the same moment in time. And only when you measure or observe it do you find it here or there. It's loose language. And it's loose language because what we really mean is before the electron's position is measured, it doesn't have a position. It's not that it's located at two places. It's that the very conception of location doesn't apply until that measurement is undertaken. So roughly you can say, yeah, it's kind of smeared out. It's hovering in both locations simultaneously. But location in physics is really something that is gleaned through observation. And until the observation is made, the weirdness is that you cannot ascribe a location to the electron. You can only ascribe a probabilistic distribution of possible locations. And that's very different from having a position, from having a location. BH 2020 asks, are atoms conscious? I don't know. What do you think? My gut reaction is no, they're not conscious. My gut feeling is that consciousness is something that emerges when a lot of atoms come together into a particular organized structure like a human brain. And within that organization, the particles can undertake processes, undertake information processing that we experience as conscious awareness. But there are some really intelligent, smart people who have come to the conclusion that maybe atoms and particles are conscious. The reason they come to this conclusion is they say to themselves, look, how can thoughtless, mindless, sensationless particles somehow come together in a group to yield sensations and reflections and thoughts and emotions? How can ingredients that don't have any of those qualities generate those qualities simply by coming together in a large group? And so some say they can't do that. The only way that you can have consciousness is if the ingredients themselves have some small amount of consciousness, proto-consciousness, and only by pooling the proto-conscious qualities can you yield the conscious experience that you experience and I experience all the time. I don't buy it. I don't buy it yet. I get the motivation, but I think it's investing consciousness with too much mystery. I think one day we'll understand conscious awareness and we'll look back at these theories and understand why people put them forward, but kind of smile and say, wow, they really thought consciousness was far more mysterious than it actually is. The first time we build an artificially intelligent being who really convinces us, which is tough, but really convinces us that it has internal conscious self-awareness, I think at that point we'll say, yeah, it's just a quality of the world that emerges from organized motion of particles. Okay, let's see. Let's see what we got here. Boy, I'm sorry. The writing on the screen has become so small. I just wish I could find a paragraph. Oh, here we go. So I can actually read this one. Okay. All right. Can you speak to whether there's an edge or a boundary to the universe? Could an infinite universe have an edge? Well, if the universe is infinite, we typically imagine that it doesn't have an edge, just goes on forever, and that's all there is to it. But, that's a strange idea. And if you really sit down and think about a universe where space goes on forever, it's kind of a breathtaking idea, but it's such an odd and strange idea because we don't encounter infinitely big things in everyday life, and therefore we don't really have a deep intuition for it. It would be much easier to picture the universe if it was finite in extent, and that could mean that it has an edge, an end. Then you'd say to me, okay, but what's beyond the edge? And I'd say nothing. And you'd say, well, nothing like empty space. And I'd be, no, nothing, truly nothing, not emptiness. Truly, there is no conception of a location beyond the edge. Now, that's a strange idea, too, because anything in the real world, if it has an edge, certainly there's a conception of going beyond that edge. So it really strains our intuition to picture that version of a finite universe, but that's possible, too. Another possibility is that the universe has kind of a circular shape to it, right? So imagine that the universe is either a large circle or a big ball, right? Then if the surface is the universe, then again, there's no edge. There's nothing that you run into, which is the end of the universe. But yet, if you keep walking, you circle around and around and around. Now you could say, well, what's off the surface of the ball? And again, I'd say, wrong question. There is nothing off the surface of the ball. I'm talking about a three-dimensional surface, so it's a little harder to picture. But it would mean that that would be the totality of reality. So the finite version is like a little easier to picture, but clearly has its own strange qualities. The infinite version is pretty perplexing to think about too. And as of today, we don't know which shape of space is the right one. Okay, what do we have here? Um, how should we understand the idea? This is coming from Marie Fatarova. How should we understand the idea that our world is just a hologram mirroring a reality happening near a black hole? Good. So this idea of the holographic universe, the holographic principle that scientists have been developing over the course of the last couple of decades, really. And it suggests the following strange picture. It suggests that this three-dimensional world that you and I inhabit may itself be the reflection of laws and processes taking place on a distant bounding surface. Maybe it's at the edge of the observable universe, a thin, distant bounding surface, which is able to fully articulate and describe everything that happens in this three-dimensional world that we experience. Now, why hologram? Well, you may be familiar that a hologram, what is it? It's a thin piece of plastic which when illuminated correctly, yields a realistic three-dimensional image. So it's a two-dimensional thin plastic yielding a realistic three-dimensional image. In this holographic universe scheme, you have a two-dimensional surface, not a piece of plastic, but you have a two-dimensional surface, which in essence is illuminated by the laws of physics, yielding, as the theory goes, this realistic three-dimensional world that we inhabit, even though there is another description, an equivalent description that's flat, two-dimensional, and far away. This idea does come from black holes, which is what Marie notes. It really comes from the understanding of what happens to an object when it falls inside of a black hole, and the notion that people like Gerard 't Hooft and Lenny Susskind and many others have put forward is that when an object falls through the surface, the event horizon of a black hole, the object kind of leaves an imprint on the surface, a kind of holographic imprint, because the object itself does fall in at least the conventional version of the story. It's been developed in other ways that would take us far afield for me to address right now. But imagine that like the object does fall in, my wallet, for instance, falls into the black hole, but it leaves a kind of shadow on the surface. And that shadow has all the information contained in the object. In principle, you could extract that information and rebuild the object from it. So you'd have a three-dimensional object that fell in described on a two-dimensional surface by information imprinted on it when the object fell through that surface. And that's like a hologram. And then the realization is that is a black hole idea, but maybe that idea can apply to the universe as a whole, with us being the objects that are on the inside, three-dimensional versions of us, being fully described by a two-dimensional version on a distant surface that surrounds us, the holographic surface. Okay, Dylan asks, if space is expanding faster than light, how does light reach us? And you're right. Einstein told us that nothing can move through space faster than the speed of light, but his theory does not in any way constrain the rate at which space itself expands. It can expand at a rate properly defined that is greater than the speed of light. And if an object is moving away from us at faster than the speed of light because space is swelling so quickly, then the light it emits will not be able to reach us. And indeed, the current accelerated expansion of space around us suggests that in roughly 100 billion or a trillion years, distant galaxies that we can currently see will be rushing away from us faster than the speed of light, and therefore the light that they emit will not be able to cross the ever widening gap between us, and we will lose the ability to see those distant galaxies, which means in the far future, when we look out into deep space, we might see nothing but darkness. And we might therefore be led to conclude that the universe is unchanging. It's static, right? It's the distant galaxies, their motion that clued us in that the universe is expanding. We saw those galaxies rushing away, but if in the far future, we can't see those distant galaxies because they're moving away so quickly, faster than the speed of light, our descendants may be lulled into thinking that they live in a static, unchanging universe, even though that's a picture of the world that we know to be false. So it's kind of a strange state of affairs. Yash Pai asks, what will happen after the Big Rip? I don't know. After the Big Rip, after sort of molecules and atoms are torn apart by this possibility, only a possibility, that the accelerated expansion of space is speeding up, that the dark energy is gaining in its force, everything will be torn asunder. Could things begin again? Quantum mechanically, basically anything not forbidden by the quantum laws that has a non-zero chance of occurring can occur if we wait long enough. And therefore, at least it's possible that the universe kind of restarts again. But now we're in truly hypothetical land, speculative realm, and I don't know how to go much further than that. Okay, what else do we have here? Brian, can you comment? This is Martin. Can you comment on the frozen river deterministic universe versus quantum uncertainty? Does this discrepancy mean that something of our understanding of time is wrong? So Martin, you're absolutely right. When we talk about the frozen river picture of the universe, we're typically thinking about it in a more classical sense. We're imagining, even using Einstein's general relativity, it's a classical theory where particles move along trajectories and objects have definite locations at definite moments in time and so forth. How would that picture change in the quantum mechanical version? Well, in a way, it doesn't need to change that much at all. Now, however, rather than talking about particle positions and velocities, you talk about quantum mechanical wave function. And so you can imagine that that wave function carries on, it develops via the Schrodinger equation, whereas particle velocities and positions, those things are governed by the Newtonian mechanics of classical mechanics. So in quantum mechanics, you just have a different equation and a different ingredient, the wave function, but you can imagine its deterministic evolution simply replacing the deterministic evolution of positions over time. And in that way, you can still have a block universe. The issue that I'm struggling to fully answer is we don't have a full answer to the quantum measurement problem. So I'm putting the quantum measurement problem to the side, imagining Schrodinger's equation is all that there is. And then you can imagine that just as in the Laplacian sense, if I know the positions and velocity of particles today, I can predict them in the future and in the past. If I know the wave function today, I can use Schrodinger's equation to predict it in the future and the past too. And that way I can invoke that block universe picture, even in the quantum mechanical setting. Okay, what else we have here? What's the best way, Yaganash asked, to learn the math for string theory? I would probably send you to the book by Barton Zweiback, An Introduction to String Theory, to sort of get the lay of the land. And then you basically need to really study differential geometry and topology and algebraic topology and algebraic geometry. There's a lot of math that you can study if this field sort of grabs hold of your passion and excitement and it's a mathematical direction in which you want to go. Dr. Brian Greene, can you please explain the relation of, I was reading the question and it scrolled by too fast. Can I get it back? It was a good one. Derek says, you touched on the theory of space being infinite. If it is infinite, has it always been so? And the answer is yeah. If space truly is infinite, it was infinite all the way through, right? Because, if you go further back in time, when the universe was half as big as it is today, which is meaning that galaxies are half the distance apart than they are today, then the extent was infinite. You cut it in half, and half of infinity is still infinity. And you just have that all the way back to the beginning. So the picture you should have in mind for the origin of the universe is not the little dot that many of us use just because it's easier to visualize. Think about the origin of the universe at time zero as being infinitely big. It's also infinitely dense. So these are the singularities that come in at the Big Bang that ultimately we need to really understand. We don't fully yet. But imagine that space is infinitely big and infinitely dense, and the whole thing expands. And our part of that cosmic expansion is emanating from one little point, if you will, on the initial infinite surface. But there are other points, and those other points are part of reality, and they contribute to the full extent of space, which would be infinite at the beginning, infinite in the middle and infinite at the end, whatever end actually means. Okay, do we still have time? Oh, we have a couple more minutes as I am starting to tire out myself, but I'd like to give you the full hour. Why not? Good. Brian Greene asking quantum mass asks, does quantum decoherence solve the quantum measurement problem? Answer, no, it does not. So quantum decoherence is a very important part of quantum mechanics in which when a quantum mechanical system has sufficient interactions with its environment, its fundamental quantum mechanical properties get suppressed and its behavior becomes ever closer to the classical behavior that we know about from Isaac Newton classical mechanics. But simply suppressing the quantum features does not make them go away. They're just less visible. So all of the weirdness and strangeness of quantum mechanics that we are aware of without thinking about decoherence is still there even when we think about decoherence. It's just highly suppressed. So what decoherence does is it tends to cause the wave description of a physical system to break up into parts that each look classical. But for instance, the quantum measurement says which one of those classical like outcomes is the real one that we measure. You still have to pick one. And without a solution to the quantum measurement problem, you're still faced with exactly the same puzzle of how to go from the realm of possibilities to the distinct singular reality that we witness. It helps the quantum measurement problem in certain ways because we now at least understand how classical behavior naturally emerges from the quantum mechanical description. But it's not the fully classical behavior, as there's still a menu of outcomes, not a single outcome that emerges from decoherence. Okay, what else do we got here? So, do I believe in God? I'm asked by Shuvik Mondal. And yeah, I mean, it's a perfectly fine question. Do I believe in God? Well, I would put it this way. I don't know whether God exists. I'm fully aware of the fact that a divine being that wanted to fully stay behind the scenes and say create this magnificent universe, but not allow us to directly become aware of the presence of that divine being would be able to accomplish that, right? If you can create a universe, you can certainly stop these little puny human brains from being able to prove your existence. So it's possible that there's a divine will behind it all. It's also possible that there's not a divine will behind it all. The interesting thing from my perspective as a physicist is this question has hardly any impact on what I do, right? I try to figure out formula equations that will give us deeper insight into the workings of reality and whether those equations were put in place by a divine being or whether they simply are there by virtue of how reality is somehow constructed doesn't really matter. I'm still trying to figure stuff out, and I'm thrilled to work out God's handiwork if that's the reality. And I'm thrilled to work out the fundamental equations if that's all there is to. Now, that's speaking as a physicist. Speaking as a human being, yeah, I would be pretty happy if there was more to reality and divine being out there. That would be an eye-opening, stunning, profound realization that I think every member of the species would find deeply impactful. All the same, if there's not a divine being, I think there's a perfectly viable path to having purpose and meaning. What is that path? We have to recognize that it is astonishing that we're here. It is a stunning fact that we are able to engage